I have to.
Okay, so thanks everyone for joining our Statistics Across Campuses seminar this afternoon, if you're in Sydney. So today we have Sebastian Ertel from the Technical University of Berlin. He's a PhD student there it's an IRTG, isn't it, Sebastian?
Yeah, exactly.
Stochastic analysis and interaction. And today he's going to talk about the analysis of the Ensemble Kalman-Bucy filter for correlated observation noise.
Okay, thanks. Thanks a lot for the kind introduction, and also thanks for inviting me and giving me the chance to present some of my research. So, okay, what you're seeing today is some joint work with my supervisor, Willem Stannert. And I should say that, well, yeah, of course, this work can now be found on the archive under this link that I put here. And I should say that, well, the paper itself is mostly mathematics, more theoretical. So the main focus is on some existence and uniqueness results and some convergence to the mean field limit. Nevertheless, I'm not going to torture you with proofs. And instead, I will sort of give you the best outtakes, what I think are good outtakes of the paper that maybe are also interesting to a general audience. Okay, so that said, maybe we'll get started. So as usual, the first few slides are just there to sort of make sure that we are all on the same page, and that what I think of the Ensemble Kalman-Bucy filter is also something that you may recognize as an Ensemble Kalman-Bucy filter. So we are working we're working as usual, as we usually like to do, in a continuous time framework. So meaning that our signal is given through some stochastic differential equation. If you're not that familiar with stochastic differential equations, think about it as basically just some ordinary differential equation, ODE, perturbed by some noise term. Here, these things, this dW and dV, you can think of these as basically just differentials of a Brownian motion, so white noise, if you will, if you're not that familiar with this with stochastic integrals. And okay, then in filtering, right, we have the signal dynamics and we observe them here. And as usual in the continuous time framework, we assume that the observations are given by some stochastic differential here. You see it as this form here. And now what I've written up here can be looked up in this book by Bain and Krishan, and it's there called the Correlated Noise Framework. And what you recognize is basically the reason why it's called Correlated Noise Framework is because the observation noise, so observation error, and the signal dynamics, well, they are correlated because they have the same part in it. And applications of this particular correlated noise framework, well, there are some theoretical applications, mainly from sort of switching regimes, and you can also think probably about some direct applications where the observation error and the signal dynamics are correlated. I'm not big on applications, so I'm not giving you an example here. Nevertheless, okay, it's a setting that is considered in the literature. Okay, and then as usual, the goal in filtering is to compute the posterior, which we will always denote by eta, and we will not differentiate between the posterior and its density. We will always assume it has a density, and we will denote it in the same way. And basically, all results that I present here can be generalized. I use this particular setting with, for example, time homogeneous dynamics and uncolored observation noise, mostly for notational convenience and brevity. Okay, then. Okay, as I said, our goal is to compute the posterior, and in the linear Gaussian setting, so where the signal dynamics are linear, initial conditions are Gaussian, then this is achieved by the Ensemble Kalman-Bucy filter. And what I will call here the Ensemble Kalman-Bucy filter is this interacting particle system. So this I here varies between 1 and m. So we have m interacting particle systems, interacting particles, interacting through the empirical covariance, pm here, and the empirical mean, xm. And the way this system achieves its goal in the linear and Gaussian case is basically for this interacting particle system approximates this mean field equation for m to infinity. So what is written above here is the mean field limit of this system down here. Okay, and now this mean field limit, this what we call McKean-Vlasov equation, because it's a stochastic differential equation that depends on the marginal loss through the marginal covariance matrix p bar, and the marginal mean m bar. The solution to this McKean-Vlasov equation has a nice property, namely that the marginal loss, which we will denote by eta bar, they are actually equal to eta. So in other words, if we are able to approximate eta bar, so the law of x bar here, through this interacting particle system, which we can do basically by considering the empirical law of this interacting particle system, then we have achieved our goal, because then we have approximated eta. Okay, so this is what I will call the Ensemble Kalman-Bucy filter in the uncorrelated setting. So here it's important C tilde equals 0. And now our goal is, for the first part of the talk, to derive an Ensemble Kalman-Bucy filter, so a version of this thing here in the correlated noise framework, so for general C tilde, or for C tilde being some general metrics. Okay, so that's our first goal. And well, one way to do this is basically to ask ourselves, well, what does the ENKBF do on sort of a macroscopic level? So what is the macroscopic view on this? What does it do on a general level? And basically it's sort of a two-step process, I would say. So the ENKBF, or here I called it ENKF, Ensemble Kalman filter, that's maybe the more the term that's more known. And the ENKBF actually approximates the posterior eta bar, eta, in at least in the linear Gaussian setting, in a two-step process. First, we derive a mean field process x bar here, which actually is consistent in the sense that its marginal loss eta bar are always equal to the desired posterior eta. And then in the next step, we approximate, we want to approximate our process x bar here through, in our case, it was through a system of interacting particles. And that's the second step. And if we have that, well, then we achieve our goal, of course. And I will mostly, for the first part of the talk, or for the most part of this talk, I will focus on the first step, actually. The second step, well, this is another story. Actually, the second step, this is also some work by Sahani. And okay, so the question, of course, the first problem that you encounter, that you have to look at if you do this two-step process is, well, then ask yourself, the question is how do you choose your x bar? How do you find this process x bar? I mean, it's also certainly this process x bar is not unique, of course. And the answer to this is that you use the Kushner's atomic equation. If you don't know what that is, you will see it on the next slide. Before that, I will just want to sort of honor those that came before. So basically everything that you see in the next few slides, this is also done in the uncorrelated setting in this paper by actually Sahani, Sebastian Ertel, and Wilhelm Stannert from 2020. And they sort of unified actually some nonlinear filters, the most prominent ones being this filter here by Krishan and Jiang, and the and Young, and the feedback particle filter, which you can find in this paper. And for the correlated observation noise setting, which we look at here, actually a filter, a consistent filter here, X bar, is also derived in this paper by Nüsken, Reich, and Rosteber. And they derive it through a slightly different methods, if you will. Mainly they note that you can switch from the uncorrelated setting to the correlated setting basically by an adaptation of the observation function, which you will see later on anyway. Okay, so as promised, first I will tell you what the Kushner-Satonovich equation is, if you haven't seen it before. So it's a stochastic partial differential equation here. Partial differential equation because we have this partial differential operator L star here, which is the adjoint of this operator L. And stochastic because we have sort of a noise through or a stochastic term through this observation dy, which is part of this innovation term or innovation process, we call it di. And it's a sort of non-linear, non-local stochastic partial differential equation because we see the non-linearity because we have here products of either the solution, and non-local because here this either t of h is just the expectation of h of the observation function with respect to our distribution either. Okay. If you don't know too much about stochastic differential equations, and this was a bit confusing, don't worry. The point is just that we have this Kushner-Satonovich equation, and in principle, and we know that the posterior evolves according to it, and in principle, we could use this Kushner-Satonovich equation to actually compute the posterior. And you can do this in the low-dimensional case. So if the dimension of our process, of our signal x is well, not too high. In practice, however, you often want to consider high-dimensional signals. They are very important for applications in meteorology and the geosciences, where the Ensemble Kalman filter is mainly used. And their sort of standard PDE solvers just, well, they are just not feasible because of the so-called curse of dimensionality. You just won't have a sort of supercomputer or whatever that is able to handle these things. Okay, and so people had to be clever, and therefore they derived different methods. One of them is the Ensemble Kalman-Bucy filter. Okay, we use this Kushner-Satonovich setting in the following sense. Namely, we have, as I said, it's a non-linear, non-local stochastic partial differential equation. And as I said, we want to find this process X bar, and write this X bar, the law of X bar, which we denote by eta bar. This should actually be equal to the posterior, meaning that it also has to evolve according to the Kushner-Satonovich equation. And again, this Kushner-Satonovich equation is a non-local, non-linear partial differential equation. And the class of processes that do that job, namely that their laws evolve according to these non-linear, non-local PDEs, are so-called McKean-Vlasov processes, or processes that are given through some McKean-Vlasov SDE, stochastic differential equation. And this motivates the following ansatz, which you can also find again in a paper by Sahani, Reich, and Stannard, which is to make the ansatz that X bar evolves, first of all, according to the signal. So that's the first part here. And then we perturb the signal by some McKean-Vlasov parts. And the reason why we do this is, well, right, if you look back at the Kushner-Satonovich equation, that's exactly what you have here. So the first part, this L star, well, that corresponds to the signal dynamics. And then the second part here, the signal dynamics are then perturbed by some non-linear, non-local part. So if this was confusing. The main part is just that we that the form of the Cauchy-Slatonic equation strongly motivates this ansatz here for choosing x bar. And now, of course, we have to find coefficients a and k that do the job. So we have to choose a and k in such a way that the law eta bar is actually equal to the posterior eta. So what we do now is then to compare the Cauchy-Slatonic equation, right? Because this thing, the law of this thing has to evolve according to the Cauchy-Slatonic equation, according to the so-called Fokker-Planck equation of x bar. And this Fokker-Planck equation is the equation that actually always describes the evolution of this eta bar, of the law of x bar. Okay, and it's this differential equation here, and actually even stochastic differential equation here because of this dy. Anyway, so the point is now we just the way we find this k and this coefficient a is basically by comparing these two equations and choosing a and k in such a way that these two equations, that the right-hand side of both equations are equal. So what you see will fall out is basically the signal part, because of course this was present in sort of both the Cauchy-Slatonic equation and of course our ansatz for x bar, and you basically have to make a comparison between the coefficient, between these coefficients and these coefficients here. And what one sees now immediately is if we compare the coefficients in front of the dy, so this thing here with this guy here, is basically that your k has to solve a partial differential equation, because here this is a first order term and it should be actually equal to a zero order term, zero in terms of the differentials. So you have to solve some PDE. You see this, and this is part of the reason for this is basically because you choose this Fokker-Planck ansatz. Okay, now you can now do what you have to do, namely compare the coefficients and then derive the form of k and a. I'm not doing this here. I basically have written here up the results, so the equation for x bar, and we go through the individual terms. So the first term of the equation of x bar is just the signal dynamics. This is not surprising because of the ansatz that we make. Then we have a first part here of the perturbation. So what you see is you have basically a sort of an innovation process here, dy minus h of x plus, then of course, then you have even the mean. The point is here, this is sort of the innovation process because it's sort of the difference between the actual observations dy and what you sort of would predict based on your process x bar. Okay, and this is multiplied by something that we call a gain term or Kalman gain, k, and this gain term k splits up in two parts. One is this k0, which is the Kalman gain term actually for the uncorrelated case, and then you just add your c tilde. So in other words, switching from the uncorrelated case, uncorrelated noise framework, to the correlated case where c tilde is some arbitrary metrics, you just have, in terms of the gain term, you just have to translate the gain by your c tilde, very simply. And what you see now is that your gain term in the uncorrelated case, this solves a partial differential equation, as I said before, which comes from the ansatz, and it's this partial differential equation. And of course, you have some choice, because you can perturb your k0 by basically any, we call them eta harmonic function, by any function which satisfies this condition here, and that's its divergence multiple of it multiplied with eta bar is 0. Okay, so that's the first term. Then you have some correction term here, and which looks complicated, but in the case that your observations are scalar, so your y is actually a scalar process, then your gain term k is just a vector. Sorry, is there a question? Okay, so I guess not. Then I will continue. So anyway, your in the scalar observation case, your gain term k is just a vector, and then this thing here is exactly the advectional derivative. So that's the nonlinearity in the Navier-Stokes equation, and we will see later on why that is. Okay, and then you have a third term in the perturbation, namely this thing here, which is an inflation term. So if you think of it as an ensemble, this will spread out sort of the ensemble members, and this is the only part which is entirely due to the correlations, right? If the C tilde would be 0, then this term here would disappear. And then again, you have some choice. You can perturb by any either harmonic function omega 0. Okay, so this you have this complicated looking equation, and especially this correction term here, which again is sort of a generalization of the advectional derivative. This motivates sort of viewing this equation through a kinematic sort of lens, namely. The question is how you can interpret sort of this K0 here. If you know what this K0 does, well, the other terms basically are all derived through K0. And one way to view this K0 is sort of through a kinetic or to take this sort of kinetic or fluid dynamic point of view and say, well, if we, maybe I go back here. If we write this equation of K0 here, which this equation 4 here, which I've written in orange, in a flux form by integration by parts, then we see what this K0 does. Namely, this K0 here is a velocity vector, if you will, or is a velocity, such that for every domain D, the total flux of particles with density eta bar and velocity K0, okay, is given by the difference of the observation in that domain D here, difference between that and the global average observation. So in other words, your K0 is sort of a exploration speed. It will always point you in those directions where the difference between the observation in those regions and the global average observation, the ensemble average of the observation, where that is the greatest. In these directions you will travel. Okay, and well, one velocity field which does the job is actually the covariance matrix. It's given by the covariance matrix times the transpose of the observation vector, and the reason for that, which is actually the Kalman gain term in the classical Ensemble Kalman-Bucy filter, and the reason for that is the following. Actually, we have this will come up 2 times. Namely, first of all, if we now assume, right, this equation which we have here, this is quite complicated, so we want to simplify it. So let us now assume that our eta bar is Gaussian. So we assume here that eta bar is a Gaussian with mean m bar and covariance p bar. Okay, then the equation that I showed you before, this complicated system, simplifies. Namely, you can actually then choose your K0 to be constant, which is exactly the covariance times H transpose, as I said before. And because this thing is constant, then the system that we have looked at before simplifies to this system here, which is looking a bit more benign. Still maybe a bit difficult because of this inverse here, but certainly a bit more benign than a system which involves partial differential equations. Okay, and this is what we call the Ensemble Kalman-Bucy filter in the uncorrelated setting, because in the linear and Gaussian case, right, this is a consistent mean field representation of the posterior. And if we would go back to the earlier slides and just here set C tilde to be equal to 0, then you see immediately that it's exactly the ENKBF that was written before. Okay, so this is for the linear and Gaussian case. So if you're linear and Gaussian, then your posterior is actually itself some Gaussian distribution, and then you see that your x bar is given through this equation here. Nevertheless, often it's even considered in the nonlinear setting. So if b is a nonlinear function, this equation here is considered 2, even though it's not consistent at this point. So even though it doesn't give the posterior. And one way to motivate this is slightly is the following, namely, actually the property of our process k of our gain term k0, that its expectation at least is given by this p bar h of t. So in other words, the expectation of this k here, sorry, here, still doesn't write now here, of this k here is exactly given by the gain term, which we have here for this equation. So in other words, if you want to say this fancy, the in the nonlinear setting, the ENKBF is actually sort of a zero order approximation to a consistent filter. Zero order in a Löwe expansion, or which probably is more relevant through some zero order in terms of polynomial projections. And that's just some fancy way of saying saying this property here, that its expectation is given by covariance times observation transposed. And therefore, well, there is maybe some slight motivation. And we could also think of using this property for doing some error estimates. We haven't even begun to do this so far. But for us, this is again some motivation why we would also consider this equation here for nonlinear B. And now, even though this equation looks quite benign here, this equation here looks quite benign, it really isn't, because it only satisfies sort of local Lipschitz conditions with respect to the right-hand side, because here you see you have a product between p bar and x bar, so you only have local Lipschitz conditions and not global Lipschitz conditions. And this turns out to be a huge problem, because actually there's no general analysis for McKean-Vlasov equations under local Lipschitz conditions. And you can even show counter examples, namely you can show some non-uniqueness results of McKean-Vlasov equations under local Lipschitz conditions. This is done in this paper of Scheutzer. So now a huge part of our paper basically now focuses on showing that this equation that we had before is well posed, so showing existence and uniqueness. I will wrap this up because I don't have that much time anymore. I will wrap this up quite shortly. So we proved here the well posedness of the equation, meaning that we proved existence and uniqueness results by some combination of a fixed point argument and a stopping time argument. And the main, I think this is probably not that interesting to a general audience. The main point here, the main step that we took, or the main tool that we used, sort of, to show existence and uniqueness, is these two inequalities here. So we can estimate the trace from above, and you see here you have the point is you have some linear estimates, and here this part here is quadratic, but it's negative, so it will always draw you sort of back to the origin. And this thing here, therefore this thing here is negative. You can drop it out, and then you get some easy linear estimates, which is much worse actually than what you would get if you let this thing in, if you keep this thing in. And actually, you can also estimate the spectrum from below. So lambda I should be the ith eigenvector of p bar. And you then get these estimates from below. And you see, if you assume that this thing here is positive, then you will always be repulsed from 0. So you will always have some positive spectrum, and you can derive uniform estimates from this. Okay, and I will wrap this up quite briefly. So we had this equation here before, where we showed, we'll go back quite briefly here, this equation before here, this x bar, where we showed existence and uniqueness. And then, of course, in the next step, as I said, the second step of the Ensemble Kalman-Bucy filter is to approximate this system here. And the way you do this canonically for a McKean-Weld equation as this is basically just writing down the equation again through an interacting particle system, where you replace the true moments, so your covariance and your mean, through empirical moments, which results in this equation here. And now a main part of our paper, finished in a few seconds. The main part, another main part of the paper is then showing existence and uniqueness of this equation here. And this turns out to be much more difficult than we originally expected, because of this inflation term here. This may become singular. You can see this, for example, for 2 particles. This term here is really just the xi minus xm divided by its norm squared. So in other words, if the ensemble collapses, so that particles are equal to the mean, then you have a problem, because then you have hit a singularity. And now what we did to prove well-postness is that under some assumptions here, you can actually show that this collapse of the ensemble never happens. In other words, you can prove that your empirical covariance matrix is actually regular, and which also requires the a bit annoying assumptions that your ensemble size is bigger than your dimension, which is not really practical. However, this is more of a technical assumption, because the equations that we have dealt with are quite well, lengthy and difficult to handle. And the main assumption that you really need is this thing here, actually, which is, again, sort of, as you see, basically the same thing as before, that you can control the spectrum from below, plus some additional term which takes care of fluctuations of the empirical covariance matrix. Okay, I will skip this and finally say, maybe I can later on, and finally say that we can also achieve some relatively weak propagation of chaos results, meaning that we can show that our particles xi converge, actually, that our particles xi converge against sort of copies, independent copies of our process x bar, and thus we can approximate the law. However, we can do this only very weakly, namely in probability, which is not that great, because, and the reason why we can only do it in probability is because we have implicit rates, because we have to sort of stop the process if the covariance gets too large, or the covariance matrix also gets too singular, then we have to stop the process. Meaning that we only get what's often referred to in the literature as implicit rates. So the takeaway from this slide here, if all this technical terms were a bit confusing, is that we actually can show that the ENKBF that we derived actually does its job, but only does it in a somewhat in a sense that that is a bit too weak for our taste, let's say. So you can greatly improve, certainly, the results, or hopefully you can improve these results. One can improve these results, which would also be sort of one of the next steps, one of the next ways to extend this work. And because I'm run out of time, let me just say that here are some references that I've used that may be useful. And of course, if it's wanted, I can also share my slides with anybody who wants it. Okay, so this will be all. And from my part, I think I've also run out of time. So yes, now if there are any questions, I would certainly appreciate that. Thanks a lot.
Thanks very much, Sebastian. That was a really nice talk. I really liked the kinematic interpretation that you gave as well. That was really nice. Are there any questions? Maybe I can get the ball rolling and ask, you mentioned error analysis and accuracy analysis. I was curious whether you have an intuition about whether the standard results in the uncorrelated case for the Ensemble Kalman-Bucy filter with nonlinear signal drift. So the accuracy analysis that's done there by de Villiers, Reich, and Stannard, whether that also, or how that needs to be modified for the correlated case, and if you think you won't get as strong results.
Okay, so in principle, I mean, we have most of the tools there. So the first problem is really for the filter that we have written down. I think it's significantly more difficult, even for the uncorrelated case, mostly because of maybe I go back here, mostly because of the same reason that we or with the same problems that we encountered here, namely that you here have a stochastic signal. So what they do, right, they consider what's sometimes referred to in the literature as sort of a transport-inspired filter, where they replace these stochastic noise terms by sort of deterministic inflation terms. And what's nice about that is that then you can then actually here in the evolution of the covariance matrix, this term here, I haven't talked about it, but this term here, this is a local martingale term. So it's a stochastic term. This actually drops out. So you have a deterministic evolution equation. And then you have some nice results that lets you sort of control the spectrum, that give you precise equation how the spectrum evolves. And you can estimate them from above and below. If you have that, then, well, I guess you can do their analysis. I have not checked that into too much detail, but I would guess, I mean, we have the same tools that they have. And actually, the terms that you encounter, you have the same problematic term, right? You have also this deterministic inflation term there. So I don't think that should be that much problem. However, of course, if you consider this, what we call if you consider our Ensemble Kalman-Bucy filter that we derived here, that's sometimes referred to as the deterministic Ensemble Kalman-Bucy filter, then this will be much harder because you have these fluctuations through this term here, stochastic fluctuations, and therefore you can't actually derive any precise dynamics, or at least as far as I'm aware, and this doesn't exist in the literature so far, precise dynamics for the spectrum, and then you have to work around it a lot. So for us, this required to sort of look at these regularized inverses, this thing here, and estimating them uniformly in epsilon to get some control of the spectrum. So I think if you consider the sort of deterministic inflation terms like they do, then it should be easier. If you want to do this for the sort of for this deterministic Ensemble Kalman-Bucy filter, then even in the uncorrelated case, I think this can be quite challenging.
Yeah, I agree. Are there any other questions? So it's almost 5 p.m. in Sydney, so everybody's, I think, getting ready for home time. But okay, Robert has a question. Go ahead.
Hi. I have to admit, I unfortunately missed most of it. Now, but this is interesting because in the discrete case, we can take this situation of correlation between the errors in the signal and in the error terms in the signal and in the state transition matrix, and turn that into a lag of y of the dependent variable in the state transition matrix. And then we've got independence. Is there anything you can do that's similar in the case you're considering?
Okay, so I'm not sure. So what you can certainly do is you can as usual switch from sort of this deterministic inflation term here, which we have here, to something stochastic if you want to get rid of this term here. So you could replace this by a Brownian motion. I'm not quite sure if this compares to what you have, and I don't know. I mean, it would be curious. It would be interesting.
Yeah, because if in the discrete case you've got a correlation, but then as long as you've got Gaussianity, you can, as I said, you can take the you can take that correlation and turn that into an extra term in lag y. That's the dependent variable, just by doing something very simple, orthogonalizing.
Okay.
And that's actually provides a fairly nice and fast solution. Now, I'm not even talking about the actual computation, particle filters, or anything else. I'm just talking about just actual structure. And of course, then depending on whether you depending on whether it's a nonlinear, non-Gaussian, nonlinear system or a linear system, you can then use the Kalman filter, or you can use the particle filter to do your filtering.
Mm-hmm.
Now, your situation is more interesting and complex, but as long as your disturbance terms are Gaussian, you might be able to do something like that.
Sure, yeah. Yeah, again, also this also relates here. Yes, if you're Gaussian, then also you can replace this deterministic, as I said before, also with sort of a Brownian motion, which makes it easier for numerics. Although, of course, you have added an additional stochastic term. Yeah, with respect to your question, yeah, that would be interesting. I mean, these continuous times equations, they one reason they are somewhat relevant is that they're sort of universal limits of the discrete case, if you let, of course, the time steps go to 0 and do this in an appropriate way.
No, they're nice because basically you can have unequally spaced data and everything else. They're very elegant. Yeah,
and I mean, then of course, what one could try to do, of course, would look at these adaptations in the discrete setting that you mentioned, and then look at the continuous time limit, if this results in something different or not. Yeah, would be interesting, I think. But I unfortunately don't have an answer directly to your question. I would have to look at these systems.
Now, when you apply the methodology, do you apply it to what sort of data? Is it discretely observed data, but from a continuous time model?
Yes. So I mean, in principle, actually, that's even in this paper by Sahani and co-authors. The consistent filter, the consistent equation here. Wait a second. You can actually even derive this for when you sort of make discrete time observations, but again, you have a continuous time model then basically you interpolate your observations here. Why? For us, because yeah, we like to work with stochastic analysis for convenience. We assumed that we have sort of continuous time data, which is of course not realistic. We have a continuous data stream. Of course, nevertheless, you could try to, I mean, anyway, if you want to approximate such a system, you would write down an Euler scheme or something like that anyway. So if you make your observations often enough, let's say, then you maybe could still work with this sort of assumptions that you have a continuous time data, that you have all the data, which of course for most practical purposes is probably not very realistic. So of course,
so let's make it a little bit interesting and say, let's take a system that you can actually represent continuous time, that you can represent in discrete time as well. It's amenable. Now, most are not. And then compare what you get to what you would get with particle filter or something. How have you tried those experiments?
I haven't, I have to admit. So for us, as I said, for us, this was mostly, since we are mathematicians, it was mostly, the main reason why I worked with this equation with this E and KBF was because it's a somewhat practically relevant, let's say, example of a McKean-Vlasic equation with local Lipschitz conditions. And then, as I mentioned, you have these mathematical problems, which are actually researched by some people at TU Berlin, that you then don't have uniqueness in some cases. And for us, this is something that we are greatly interested in, looking at, well, what are the boundaries, sort of where you can, what is the most general setting that you can write down, sort of, where you still have existence and uniqueness on the local Lipschitz conditions. So meaning for us, it was more, we approached this from a very mathematical point of view, sort of, with from that in mind. So we didn't have any applications in mind or any sort of numerics. The paper unfortunately also doesn't contain numerics. So for us, yeah, we didn't ask the question, I have to admit. So
okay, but nice stuff. You've got a working paper on this, or?
Yeah, exactly. So yeah, you can find it on the, wait a second, go to the first slide. You can find it on the archive under this number. As I said, it's mostly mathematics. Most of the parts that are presented here are in sort of I think it's the third section or something like that, with these interpretations, fluid dynamic interpretations and stuff like that. That's okay there. But later on, I'd say, I don't know, 2/3 of the paper are mostly devoted then for mathematics. Maybe it's still useful because we derive some estimates and stuff like that, but yeah, mostly mathematics.
Thank you very much. I'll take a look. Thank you.
Oh, thank you.
Okay, great. It looks like there aren't any more questions, so maybe we can all thank Sebastian once again for his really nice talk, and yeah, we can close the session.
Okay, then bye and a great weekend to all of you. See you.
Bye.